Okay. So I will share my screen with them. Okay, can I get your response whether you can see my screen, whether you can hear my
Yes, doctor.
voice? Very clear,
Yes,
okay?
doctor. Very
Clear,
clear.
clear,
Okay,
doctor.
okay,
Clear
thank you for
there.
the response. Okay, thank you for the response. Okay, so actually we have learned about FM signal generation. So for signal generations, this happens in the transmitter. Okay, and this is also related to your project actually, where you need to design the transmitter and the receiver system. Okay, so basically the modulators the modulator system in the transmitter can be divided into direct FM and also indirect FM. Okay, so the word direct here means that we are directly do the process of frequency modulation. Okay, and in this case, we are actually indirectly do the process of phase modulation. Okay, so because FM and PM are related to each other, so whenever we change the frequency of the carrier, we are actually changing the phase of the carrier as well. Okay, so there are many types of direct FM modulator circuit in the market. Okay, and in your notes, in your lecture notes, we only include two types of direct FM modulator, which is the first one here is what we call as the varactor diode. Okay, the picture on the right. Okay, so the picture on the right is one of the uh, direct FM modulator circuit. Okay, so for the direct FM modulator, so direct FM means that the input will directly change the frequency of the carrier. Okay, so that means the input will directly change the frequency of the carrier. So we are directly change the frequency in this case. So if you see from the modulator circuit on the right side, okay, modulator circuit on the right side, this is what we call as the varactor diode. One of the types of modulator that are frequently used in the market. Okay, and you see that here the input is put inside from the base of the transistor. Okay, the transistor is over here, and the collector is VCC is at above part, and here over here is the emitter. So again, for the transmitter, transmitter also act as a switch, which means that the switch will on and off based on the voltage at the base of the transistor. So if the voltage in the transistor more than the threshold voltage, that means the current can flow from collector to the emitter side. Okay, and in this case, we have R1 and R2, which will add to and subtract with the modulating input signal. Okay, and then it will also change the capacitance of VD1 and also frequency of the crystal control oscillator. Okay, so positive alterations of positive alteration of the modulating signal. That means positive cycle. So during the positive cycle of the modulating signal, this will increase positive alteration of the modulating signal increase the reverse bias on VD1 and increase the frequency of the oscillation. Negative alteration of the modulating signal decrease the oscillation of the frequency. So that means during the positive cycle of the modulating signal, the output that produced from this varactor diode will move from FC until FC plus delta F. Okay, so during the alteration of this from 0 until peak amplitude, that means the carrier move from rest frequency to the maximum frequency. And again, when the input modulating signal, input message signal, move from positive peak towards negative peak amplitude. Okay, so this is a VM, this is a minus VM. So when the modulating signal moves from positive peak towards negative peak amplitude, so what happened is that, so before that, the signal will go through the zero x-axis, zero crossing. So at this point, FC will be at FC, rest frequency. And when the modulating signal goes from zero crossing until negative peak amplitude, which is minus VM, so the output frequencies produced by the varactor diode would be FC would be at FC plus delta F, the maximum, and so on. So in this case, what the varactor diode will do is actually it will produce output with frequency variation based on the amplitude variation from the input. Okay, so that means the amplitude variation from the input will produce frequency variation at the output. Okay, maknanya perubahan amplitude pada input menghasilkan perubahan voltage at the output. So that means voltage variation at the input will produce frequency variation at the output. Okay, so this is the varactor diode. So varactor diode also will be one of the question in the final exam, where you need to know that this is one of the types of modulator for the direct FM. Okay, and we have the second type of modulator circuit, which is what we call as the indirect FM. So indirect FM means that we are indirectly do the process of frequency modulation, where in this case, we are actually do direct phase modulation. Okay, so that means we are actually do the process of phase modulation, where it is actually indirectly do the process of FM. Okay, so in this case, we are actually do the process of PM, phase modulation. Okay, in a simple word, we do the process of phase modulation, and at the same time, this is indirectly do the process of FM. Okay, so in the indirect FM, what you will produce is actually narrowband FM. Okay, so how do we do this? Okay, so first we need to integrate the input signal. Okay, the input signal with the oscillator, and then this will produce the narrowband FM. So you see that here, so the word integrate here means that we do the integral process of theta prime t dt. Okay, because we want to find the theta t. Okay, so theta t is actually equal to theta prime t. So we do the integral process of the input, okay, and we will produce the narrowband FM. Okay, so what we produce from the output is actually narrowband FM, which has a small bandwidth. Okay, and narrowband FM does not have many applications that we can use. So for the commercial application, normally we use a wideband FM. So in that case, we might need to have additional components after the modulator in order to produce the wideband FM. So one of the method is to use a multiplier, which um, which will multiply the frequency in order to produce the wideband FM. Okay, so frequency multiplier is one of the method to increase the frequency from the narrowband to become the wideband. So remember that narrowband means that small bandwidth, wideband means big bandwidth, wider bandwidth. Okay, so you will see later about the frequency multiplications. This is where we will learn about the up conversions process. Okay, the up conversion. And this is the block diagram of indirect FM. Okay, indirect method for generating FM signal, which means that we are directly do the process of PM, phase modulation. Okay, so you see that here, the picture above here, we have, so this is what we call the indirect FM modulator. So this red color that I highlight here is actually this one. Okay, the picture below here is actually this one. Okay, and the signal that we produce at the output of the indirect FM is the narrowband FM, NB FM. And if you want to make it as a wideband, that means we need to add additional frequency multiplier so that it will produce wideband FM. So wideband FM is the commercial FM radio broadcasting system that we use frequently in our daily lives, in our radios. So normally we listen to the radio station. It is under the category of wideband FM. Okay. So about this picture, we have asked this in the final exam in the previous semesters. Okay, we have asked this. We have asked question about this picture, where we ask the student to produce the equations at the output of each point. For example, produce the equation at point A, at point B, for example, over here, and at point C over here. Okay, so I will show you the solution for this. Okay, sorry. So I will show you the solution for this. Sorry, before that, I heard that many students want to. Is it? Okay. Okay. So if you have friends that unable to join the class, maybe because I did not admit. Wait, Okay, so if you have difficulties, if your friends have difficulty to join this class, please let me know, because I'm not sure whether I need to admit into the meeting room or not. Okay, because normally you can join the meeting without me to admit by myself. So sometimes in the previous semester, sometimes the students are unable to join because I forgot to admit. Okay, so if you have friends that unable to join because of the admission process, please let me know. I will admit in the Microsoft Teams. Okay. Again, can I get your response? Can you hear me? Can you see my screen?
Yes, Doctor.
Yes, Doctor.
Okay.
Can.
Okay.
So,
Okay. Thank you for the response. So, in the previous semester, we have asked these questions to the students about the picture below. Okay, where we ask the students to produce the equations and then uh, to to draw the spectrum and then to find the power. Okay, so again I will show you, because I have done this in the class on Monday, last Monday. So I will show you again. So the input here over here is the carrier. Okay, so the carrier in this case is, you see, the AC cos 2 pi fct. So this is actually VC cos 2 pi fct. Okay, the carrier. And the input to the integrator is actually the message signal or the modulating signal, which is 2 pi kf mt. So this is actually 2 pi kf. So mt is actually vmt, which is vm cos 2 pi fmt. So how do I know this? Because in the question we will give you the equations. Okay, we'll give you the equations, and you just need uh, to modify the equations to find the output. Okay, so as I mentioned previously, that if you want to choose whether to choose a sine or cosine. Okay, so if you ask me, I suggest you to make it similar. If you want to use carrier as a cosine, then use the modulating signal as cosine as well. If you want to use carrier as a sine function, then use the modulating signal also as a sine function. So that easy for you to calculate. Okay. So this is the input. Okay. So now let's see what happened to the carrier. So the carrier will go through the phase shifter. 90-degree phase shift means that the signal will be delayed for 90 degrees. So that means phase shift 90 degree for cosine will produce sine function. So that means the output of the phase shifter would be Vc sine 2 pi fct. Okay. And here for the integrator, you see that the integrator will do the integration process. So integral of cos will produce positive sine. Okay. So that means what we will produce is actually 2 pi kf vm. Okay. Sine 2 pi fmt divide with 2 pi fm. Okay. So 2 pi and 2 pi can be cancel out. So you have here is kf vm over fm, which is equal to beta, the modulation index. So this is actually equal to beta beta. So that you can put just beta sine 2 pi f m t. Okay, you can put beta f or you can put beta. It's up to you. No problem. As long as we know that it is a beta parameter, the modulation index. Okay. So now we have sine for the input. Here is sine 2 pi fmt. Another one is sine 2 pi fct. Okay. So you see that here is the narrowband phase modulator. You see that the symbol is X. Okay, so the symbol X here means that uh, this um, this system will do the process of multiplication in mathematics. So that means what happened at point A, the output is, it is actually multiplication of both input, okay, sine and sine. So that means we will produce beta VC sine 2 pi FCT sine 2 pi FMT. Okay, so again, according to trigonometry identity, sine and sine, you can simplify the equations to become cos minus cos. Okay, so again, using the trigonometry identity, you can do this like, you can do it like beta VC over 2 in bracket cos 2 pi FC minus FM T, the lower sideband, minus cos 2 pi FC plus FM, the upper sideband, and then close the big bracket. Okay, so this is the equations at point A. What about in point B? So in point B, again, this will go through the point B. Point B will be the same as the input, which is VC cos 2 pi FCT. Okay, so again, at point C. So what happened at point C? Point C means that you will add both A plus B. So point C is equal to A, point A plus point B. Okay, so point A plus point B, that means we can rearrange the equations to become a complete equations. So maybe I will do here, maybe. Okay, I will put here. So C. So at point C, okay, at point C, what happened is that the output gonna be VC cos 2 pi FCT plus, because we plus with the other part. So this is actually beta VC over 2 cos 2 pi FC minus FM T. So the lower sideband, and then minus beta VC over 2 cos 2 pi FC plus FM, the upper sideband. Okay, so this is the final equation at point C. Okay, so after you get the complete equations, then you're going to see that this output is similar with the output that we produce in the double sideband full carrier. Okay, which is we have upper and lower sideband and also the carrier at the center. So after we know the equation, then we can draw the spectrum. Okay, without knowing the equation, it is impossible for us to draw the spectrum. For example, here the frequency spectrum V versus F. So I can draw that. You see that I have three components. The first one is the carrier FC, and I have the upper sideband, which is FC plus FC plus FM, and I have the lower sideband located at FC minus FM. And I know that the amplitude would be VC for the carrier, and here for the sidebands is beta VC over 2. This is beta VC over 2. Okay, so from here, from the frequency spectrum, then I can determine how much is the bandwidth. So the bandwidth would be equal to FM plus FM, which is 2FM. How do I know this? The distance here is FM and also FM, so it is 2FM. Okay, and then I can also ask you how much is the power, total power. So total power, again, you need to add all the power component in the spectrum, which is P total equal to PC plus PLSB plus PUSB. Okay, PUSB. Okay. So in this case, you need to find PC is VC square over 2R. P lower sideband would be equal to beta VC over 2 square over 2R. Okay, so that means again, if you want to find the PLSB, PLSB or PUSB, which is a PUSB, this is equal to beta VC over 2 square divided with 2R. So this is for the power of the lower sideband. And then again, for the carrier power PC, same equation, VC square over 2R. Finish. So previously we have asked up to the power calculation for this. Okay. So if you look from the question banks, then you know how to answer the question based on my explanation. Okay. So if you have question about this, you can ask now. Otherwise, I will move to the next topic. Okay, kalau ada soalan, you are most welcome to ask. So, no questions? Okay, betul no question. So, if you see from here, we are producing a narrowband FM, which is equivalent to double sideband full carrier. So now the issue is we want to make it as wideband FM, which is suitable for the FM broadcasting, commercial FM broadcasting. So we need to add additional frequency multiplier. We need to increase the frequency from narrowband to wideband. So the process is what we call as the up conversion. Okay, up conversions means that we increase the frequency. So there are two types, there are two methods that we can do for frequency up conversions. The first one is heterodyning. So heterodyning means that we mix two signal, okay? We mix two signal, or mathematically we multiply two signals so that we can have an upper and lower sideband. So we're gonna take the upper sideband, which is the higher frequency. That's the process of heterodyning. So heterodyning means comes from the word heterodyne, means mixing. Okay, and the other part is the other method is to use a multiplication technique. Multiplication means that we use a frequency multiplier, which has the frequency multiplier factor. So which we will see the difference both of these methods. Okay, so you see that. So here consists of two pictures, left and right. Okay, so picture on the left. So we start with the picture on the left is using the heterodyning process. So heterodyning here means that we are using a balance modulator which receive the input, okay, the input from FM or PM modulator. Okay, input here over here is from FM or PM modulator circuit, which is from the narrowband FM. And here is the other input is we have the input from the oscillator. Okay, so the oscillator will produce the oscillation frequency or the RF frequencies that we will mix with the input signal. Okay, so you see that what balance modulator will do is actually it will do the process of multiplication in mathematics. So that means we're going to have upper and lower sideband. Okay, so we're going to have the output of balance modulator would be uh, FRF plus FC in, or it will also produce FRF minus FC in. Okay, so here you see that the balance modulator produces two parts, upper and lower sidebands, and then here we have filter, band pass filter, and you see that here it will select the sum frequency. So the sum frequency here means that it will choose the sum frequency or the upper sideband. Okay, and you're going to see that what are the characteristics of the heterodyning process. So for the heterodyning process, you see that what are the difference? Okay, so you see that from here, we have there are a few modulation parameters that we need to see at the output. You see that here we have the input is f, the carrier, the frequency deviation. This is the VMT. Okay, this is the VMT. Wait, sorry, this is the modulation index. So this is the modulation. Sorry, M in is the mod. Sorry, this is a modulation index. Here is the input frequency, modulating signal frequency. Here is the bandwidth of the input. Okay, so for the heterodyning process, what happened at the output? At the output, you're going to see that the carrier frequency at the output would be increased by FC in plus FRF. And delta F, frequency deviation at the output, remains the same as the input. And then the modulation index is the same. Okay, same modulation index. Input modulating signal, same as the output modulating signal. No change in the frequency of the modulating signal. And the bandwidth also remains the same at the output. Only the carrier change. Okay, that means the carrier has been up converted frequency. Okay, and let's see the other methods, which is the multiplication method on the right side. Okay, so picture on the right shows the multiplication process. Okay, where we have what we call as a frequency multiplier with a factor of n. Okay, so that means this component, this element will multiply the input frequency by factor of n. How much is n? It depends. Okay, depends on the equipment. Depends on the system. It can be 10 or more than that. Okay, it depends. So you see that the input, again, we will see the important parameters. What we want to see, the changes. We will see the carrier. We will see the frequency deviation delta F, modulation index. M here is a beta, so don't be confused. M is also beta. Here is the input modulating signal, and here is the bandwidth. Okay, so there are differences. There are the output produced by the frequency multiplier is different from the output produced by the heterodyning process. So you see that what happened at the output? All the frequency at the output will change. You see that for the carrier at the output will be multiplied by n factor. Okay, similar with the frequency deviation at the output, delta F output would be equal to n times the delta F input. Okay, and then what? The modulation index at the output will be n times the modulation index at the input. And this is the input modulating signal. The modulating signal at the output would be the same as the modulating signal at the input. Only this parameter will remain the same. Okay, so that means the modulating signal frequency does not change during this process. Okay, only the carrier component will change. And what about the bandwidth? So the bandwidth at the output gonna be larger than the bandwidth at the input. Why it is larger? Why not n times? Okay, again, this is the bandwidth is determined by the modulation index beta, okay, which is this one, beta. So beta, we need to check from the Bessel table how much is the beta. From there, we can determine how much is the bandwidth. So of course, if the modulation index is increased, that means the bandwidth will also increase. Okay, remember, if you see from the Bessel table, the higher the modulation index, that means the wider would be the bandwidth. Okay, the larger the modulation index, the wider would be the bandwidth. Okay, and let's see for the example. Okay, let's see for the example. Uh, so you see that this is example of the up conversions. So we are given a delta F 3 kilohertz. We are given beta 0.3, carrier frequency 500 kilohertz. And then what? Determine the carrier frequency and modulation properties. So what are the modulation properties? Modulation properties are these parameters. Okay, you can see the modulation frequency deviation. You can see the input modulating signal frequency, the bandwidth, and so on. Okay. So from here, the first question asks you to determine the modulation properties if we use the heterodyne process. The second question is about we need to determine the modulation properties if we use a multiplication process. Okay, so the first question asks you to determine the modulation properties if we use a heterodyne process that has a balanced modulator and bandpass filter tuned to the sum frequency. That means we're going to take the upper side frequency, and given the RF carrier here means that the oscillator frequency, which is 99.5 megahertz. Okay, so RF carrier here means from this part, from the RF oscillator. Okay, so from here, you see that the other parameters. So we have a delta F. Delta F is equal to 3 kilohertz. We have beta 0.3. Okay, and then we have FC is equal to 500K. RF is 99.5 mega. RF is equal to 99.5 mega. So from here, actually we can determine the how much is FM, right? So if you see from here, FM, frequency, modulating signal frequency is actually equal to delta F divide with beta. Okay, because beta is equal to delta F over FM. So therefore, FM is equal to delta F over beta. Okay, so 3 divide with 0.3. Okay, so 30, sorry. 3 divide with 0.3. So we're gonna get 10 kilohertz. Okay, 10 kilohertz. And what else I can determine? I can also determine the bandwidth if I'm using the Carson. Because if you see from Bessel table, I think there's no 0.3, if I'm not mistaken, from your Bessel table. So what we can do is actually we can find the bandwidth using the Carson. For example, bandwidth is equal to 2 times delta F plus Fm. Okay, so this is 10 plus 3, 13 times 2, 26. Okay, 26 kilohertz. This is if I'm using the Carson. Okay, so now I have all the input. I have all the input modulation parameters. Okay, so if I want to do the first question, question number 1. So I can determine that FC out. So FC out is equal to FC in plus FRF. Okay, because we are going to take the upper frequency. So this is 500K or 0.5. Actually, 500 kilohertz is actually 0.5 megahertz. Okay, 0.5 megahertz plus 99.5 megahertz. So this is actually equal to 100 megahertz. Okay, 100 megahertz. And the rest of the parameter would be the same. Okay, so the delta F out is equal to delta F in, which is 3 wait, so delta F out is equal to delta F in, which is equal to 3 kilohertz. And then what else? Beta out is equal to beta in, which is 0.3. What else we can determine is the FM in. FM in is equal to FM out, which is 10 kilohertz. And then what? I can determine the bandwidth. So the bandwidth also the same, bandwidth in equal to bandwidth out equal to 26 kilohertz. Okay, so the bandwidth, don't worry about that. I'm using the Carson. If we can use the Bessel, then you can use the Bessel, no problem. Okay, so this is for the first question. Then for the second questions, okay, second questions is to use the frequency multiplier. That means we are given a factor of n equal to 10. So that means here we need to multiply all the input frequencies. Okay, so that means FC out is equal to 10 times 10 times 0.5 mega or 500K, 500 kilohertz of input. So this is 5,000, so 5 megahertz, 5 megahertz. And then delta F out out is equal to 10 times delta F, which is 3K. So 10 times 3 kilohertz. So we have 30 kilohertz. And then what else? Beta out. So beta out is equal to 10 times 0.3, 0.3. So we get here 3. And then modulating signal at the output is equal to the input, same as the input, which is 10 kilohertz, no change. Okay, and then what? What about the bandwidth? Bandwidth at the output is equal to how much? So for example, here I'm using Carson, so I can still using Carson in this case. So you see that delta F is changes. So you see, I can calculate 2 times delta F is 30, 30K plus 10K. So 40K times 2, so I get 80 kilohertz. Okay, because delta F is already 30 kilohertz. Modulating signal frequency similar with the input 10 kilo. So we have 80 kilohertz at the output. Okay. So do you have any questions you want to ask regarding this frequency up conversion? Ada soalan? Can I get your response? Are you still there?
Yes, Doctor.
Okay.
Yes, Doctor.
I'm worried because you are too quiet. Okay. So if you have question, please ask. If you don't have question, I can move to the next topic. Okay. If you don't have question, I will move to the next topic. Okay.
Doktor,
Yeah.
boleh
Yeah.
tak kami dapat yang slide doktor yang conteng-conteng?
Yang conteng ni?
Yes.
Boleh. No problem. Or you want the video? Because I'm
Video pun
recording
okey
the
je, tak ada
video.
masalah.
Video
Yeah, because I'm recording the video. Now I'm recording the video. So I think you can see from the video because the video I will share in the YouTube later. Okay, if the video is not function, I will share the slide. No problem. Okay. Okay.
Okay,
So okay.
Doktor,
Yeah.
nak tanya untuk FM tu dia tak perlu kali 10 eh?
Tak perlu. No need. Because you see from here, for this, if you see from here, yang ini yeah. For the multiplication method, kita tak perlu multiply dengan 10 kerana hanya ini saja yang berbeza. Only this part remains the same, whereas the others will change. This is for the multiplication method. Okay, different from the heterodyning method. In heterodyning method, only the carrier will change, whereas the others remains the same. Okay, this is the modulating signal because modulating signal input is far previous process. Okay, dia adalah input from the transmitter actually. Okay, input to the transmitter because this is happens within the transmitter's system where we already done the narrowband modulation. We have done the indirect FM modulation. Then we insert to the frequency multiplier. So in this case, the input signal does not affect in this process. Sebab input modulating signal itu dia dah jauh daripada awal tadi dia dah masuk dalam sistem, kita dah buat proses indirect FM modulation. We produce a narrowband FM, then we put inside the frequency multiplier. So the frequency that we're going to modify is actually related to the carrier actually. So it does not change anything from the modulating signal part. Okay. Is it okay? So if you have question, you are most welcome to ask. Otherwise, I will move to the next topic. Okay. So the next topic is about FM demodulation. So FM demodulation is the process happens at the receiver. Okay. So at the receiver side, you see that when we transmit the FM signal from transmitter to the receiver. If you remember in the AM process where we do the demodulation process, at the end of the receiver part, okay, because at the beginning of the receiver we have many types of many other processes. We have the tuning process, we have the down conversion process, we have the filtering process to convert into IF, and then the last part we will do the demodulation process. So this is also similar in the FM receiver. So in the FM receiver, because the input to the receiver is a signal, FM signal, which change in terms of frequencies. So now what we need to do is we need to convert the input, which varies in terms of frequencies, to become an output that varies in terms of amplitude. Okay, so now we receive input signal to the receiver, which varies in terms of frequency, because we receive FM signal we receive. So the signal that we receive varies in terms of frequencies. Now we want to produce the original signal, which is a VMT at the output. So the frequency variation at the input must be converted into the amplitude variation at the output. Okay, so that means they're going to be a process of changing frequency variation into amplitude variation to the output. Okay, so you see that this graph, just to show you that for the input variations, the input signal varies in terms of frequencies from FC until FC plus delta F, and then FC towards FC minus delta F. Okay, so you see that whenever the input signal change in terms of frequencies, we're gonna produce the output like this. So for example, if the frequency move from FC until FC plus delta F, so the output that we will produce is like this, okay, towards positive peak amplitude. And whenever the input signal varies towards the lowest frequency, that means we're going to produce the output with amplitude towards negative peak voltage. Okay, so for this topic, this will come out in the final exam as well, about the demodulation process, which is the question is very easy. Okay, just you need to know about a simple process of the demodulation. Okay, so for the demodulation, there are many types of demodulator circuit in the market. Okay, there are many types, and we put some of it in the lecture notes. Okay, the first part is the slope detector. So slope detector is the simplest form of tuned circuit frequency discriminator. So it has a single slope and has the most non-linear voltage versus frequency characteristic. So this is not a very practical circuit that we use in the market actually. So this is for certain types of applications only. And if you see from here, the slope detector consists of a tune circuit and also a detector circuit. So this is the this is the slope detector, so which consists of a tune circuit. Okay, this is the tune circuit, and this is the peak detector circuit. So the tune circuit will tune to the frequencies of the input, and from here we will detect the frequency changes to produce the output variations, voltage output variations. And you see that LA and CA are the tune circuit that produce the output voltage proportional to the input frequency. Okay, and you see that the maximum voltage at the resonant frequency of the tank circuit FO and its output decrease proportionally as the input frequency deviates above or below the FO. So FO is the resonant frequency. So this is related to the frequency response curve of the circuit, which is like this. You see that the center would be the resonant frequency. So resonant frequency is the frequency that you tuned. For example, I want to listen to radio station A. The frequency is 104.5. So that is the resonant frequency, the frequency that I tune my radio. Okay. So at the resonant frequency, it will produce the highest possible voltage versus frequency curve in this example. And then if you see that the circuit is designed so that the IF center frequency, FC IF, center of IF, falls in the center of the most linear portion of the voltage versus frequency curve. So when the IF deviates above the FC center of the IF, the voltage will increase, and when the IF deviates below the center of the IF, so it will the voltage will be decreased. So you see that this is related to the intermediate frequency. Remember that during the demodulation process at the receiver part, we will down convert the frequency from RF to the intermediate frequency. So that means the center of the RF would be converted into center of IF, and the frequency is changes. So whenever the frequency is changes, it will produce different voltage at the output. Okay, so if you see from this picture, so this is the center of IF. So whenever the input signal deviates above the center of IF intermediate frequency, what we will produce is actually the maximum voltage at the output. And whenever the input frequency varies from center of intermediate frequency to the lowest, for example, this one, this will produce the lower voltage. Okay, the minimum voltage at the output. Okay, so the output will decrease. Okay, and then what? So the tune circuit converts frequency variation to amplitude variation. So the tune circuit is this one. This is the tune circuit, which convert the frequency variation to amplitude variations. And now the DIs, the diode, CI, capacitance, and the resistance RI, it will make a simple peak detector. Remember peak detector in the AM. So peak detector will do the process of demodulation. Okay. So now once the tune circuit, okay, once the tune circuit has converted frequency variation into amplitude variation, then we can do the demodulation process similar with the AM process. Okay. The tune circuit convert frequency variation input into amplitude variation at the output. Okay, so this part, the tune circuit. So tune circuit has convert frequency variation into amplitude variation. Now we can do demodulation using peak detector. Peak detector here is the similar detector, similar demodulator part like we learn in AM. Okay. So So the peak detector converts the amplitude variation into output voltage that varies at the rate equal to that of the input frequency change. Okay, so this is similar like the AM diode detector that we have learned previously. So this has disadvantage. The gain is reduced, difficult to achieve a linear slope response. So in the final exam later, we're going to ask about this slope detector, where you need just to have a basic understanding about the slope detector. So this is important for your final exam. Okay. And if you look the other types of demodulator is what we call as a balanced slope detector. So balanced slope detector consists of two slope detectors. Okay, so now for balanced slope detector, it has a upper part and lower part. So you see that for the frequency response curve, the difference with the slope detector is that the output at center of the IF would be 0. Okay, it will be 0 volt. Okay, so this is what we talking at the IF region, IF regions. At this point, at FC of IF, this is IF, center of IF, the output voltage would be at 0 volt. Different from the slope detector, it has a output. Okay, it has a certain output. For the balance modulator, at center of the IF, it will produce 0 volt at the output. And whenever the frequencies varies from center of the IF until FC plus delta F, it will produce output with towards maximum peak. Okay, maximum peak. And when the input signal varies in terms of frequencies from center of IF until FC minus delta F, okay, so the output will produce output voltage will be decreased towards negative peak. Okay, so this is the maximum here is FC plus delta F. This is this is in the IF region. In the IF regions, similar with this one, FC minus. Sorry. So the thing that we're talking about here is now in the IF regions. So we are not talking in the RF regions. Remember, the demodulation process happens when we have down convert the frequency from RF to the intermediate frequency. After we down convert the frequency, then we can do the demodulation process. So this that we learn now is actually related to the demodulation process, which is the end process in the receiver part. Okay, where we are dealing with the IF frequency, intermediate frequencies. Okay, and so balance slope detector consists of two tune circuit which perform FM to AM conversions. So as I mentioned that at resonant frequency, the output is 0 volt. Okay, the IF deviates above the center frequency, which produce a higher voltage. So you can produce a positive output. And if the frequency deviates below the center frequency, it will produce a negative V out. Okay, so the advantage of this circuit is simple and also has a disadvantage of poor linearity. Okay, so this is about the balance slope detector. And the third types of demodulator circuit is what we call as a PLL. Okay, so this is number 3 actually. The third type of demodulator is what we call as the PLL phase lock loop. Okay, so PLL is I can say that this is one of the most practical or most among the popular demodulator FM circuit, which also used until now in the practical system. Also now we still use a PLL, but PLL has many versions, many types, depending on the applications. Okay, so PLL probably is the simplest and easiest to understand. And we have asked this question in the previous final exam. So PLL also has been asked a few times in the previous semester's final exam, where we asked the students about the process happens at the PLL. Okay, so what are the questions that we asked? Actually, we asked these three processes. Okay, so PLL has three operating states, which what we call as a free running, capture state, and also lock state. So during the free running state means that the PLL tries to find the input signal. Okay, it tries to find the input signal. So whenever it finds the input signal, frequency, it will lock at that. It will capture that frequency. Okay, free running means that there's no input signal. Okay, sorry about that. No external input frequency. And whenever there's a capture state, when a capture state, that means we have the input signal, and the PLL is tries to find the frequency that we want. So that is during the capture state. Capture state means that we have the input signal to the receiver, okay, input to the receiver, and the PLL is in the process of acquiring the frequency that we need. Okay, for example, I want to listen to radio station 104.5. So the PLL will try to acquire that frequency. It will try to find the frequency, whether that frequency is available in the input or not. Okay, so whenever the PLL when the PLL find the frequency that we want, it will be at the lock state. Okay, so now the PLL already find the frequency, which is, for example, 104.5. So it will lock at that frequency. So the means a lock state means that the PLL will lock at that frequency. So it will start, whenever it lock at that frequency, it will follows the variations of the input and produce the output. Okay, so this can be this explanation actually can be seen from this block diagram actually. So again, maybe I want to repeat again. Free running state means that there's no input to the receiver. The receiver has no input. That means the oscillator runs at rest frequency. And then during the capture state means that we have the input to the receiver. So the receiver now has the input. We don't know how much, we don't know about the input. There are many frequencies at the input of the receiver. So the PLL is in the process of acquiring the frequencies that we need. Okay, for example, I want to listen to radio station 104.5. So it will be try to find that frequency. Okay, that is the capture state. It try to capture that frequency. Then whenever the PLL find that frequency that we want, it will lock at that frequency. So the terms lock here means that it will what we call, the terms here lock means that it will focus at that frequency and it will track the movement of the frequency variations. So if the frequency variations, it will produce the output voltage variations. So if you see from the block diagram, this is the simplest block diagram. Okay, so the block diagram here, if you see the block diagram of PLL. So this block diagram we haven't asked in the final exam yet. Okay, kita belum pernah we haven't asked this question yet. But this has been explained in the Wayne Thomas's book. So if you see from here, the input to the PLL, this is the FM input, where this is phase detector. We put inside the phase detector. So this is a PLL. So it put inside the phase detector. So the phase detector will compare the FM input and the frequency from the oscillator, which is FO. Okay, so what happened to the what it will produce is actually you see that it will compare, for example, this is a FI. So phase detector will compare this I or FO minus FI. It will track the changes, okay, and this will be multiplied with the transfer with the sensitivity parameter KD, and this is equal to VD. So VD is the V difference, which is this one, okay, and here, and then it passed to the low pass filter, which has a parameter transfer, which has the sensitivity parameter of, for example, KF or KL, for example, low pass, for example. So the output here would be VD times KL. Okay, and then what? Put inside the amplifier. Amplifier has a parameter of Ka. So this will multiply with another Ka. So that means this one would be KL multiplied with Ka multiplied with Vd. So this is V out. Okay. So this also will be put again to the VCO. Okay, which has, again, it also has a what they call a parameter over here. It depends on whether K or whatever parameter over here. So the VCO will the VCO means that the VCO will track the changes of voltage and produce frequencies difference at the output. Okay, if let's say there's no input to the VCO, for example, the output gonna be at neutral frequency Fn, and whenever there's an input to the VCO, it will compare the voltage from the previous, and it will produce the output, okay, which is O. And then we repeat again the process. Okay, so this is how we see the process happens within the PLL. Okay, so the input, you see that it will compare the frequencies or the phase and produce voltage at the output. The voltage is feedback to the VCO, which produce the frequencies difference. Okay, frequency, some frequencies at the output, and we compare with the phase detector again. So this is what happened in the PLL. Okay, and this also has been explained in this explanation is over here. So you see that V out is equal to delta F KD over KA. What is delta F? Delta F is the frequency difference. Okay, so if you see frequency difference is this one, delta F, the frequency difference. And if you see from other literature books, they also use delta theta, either frequency difference or phase difference. Okay, and then super heterodyne receiver. So let's look into this super heterodyne receiver. So FM also has a super heterodyne receiver, which has a universal standard for intermediate center frequency at 10.7 and also 455 kilohertz. So you see that, if you remember for AM, if you remember for AM, the standard for IF frequency, center frequency, would be at 455 kilohertz. This is what we have learned in the AM. If you still remember that whenever we do the down conversion, the center would be at 455. So for AM, the frequency band is 570, if I'm not mistaken, until 1650 kilohertz. So we just need to do only one down conversion to the intermediate frequency is enough. However, for FM band, the frequency is very high, between 88 megahertz until 108 megahertz. So in this case, we cannot do a simple down conversions like what we did in the AM. So in FM, we need to do 2 times down conversion. Okay, so the first IF center would be 10.7. Okay, the first IF center, IF1 center, would be at 10.7 megahertz. This is the first down conversion. Then we down convert again to the second IF. So the second IF center would be at 455 kilohertz. Okay, so in FM, we need to down convert 2 times. We down convert to 10.7, and then we down convert into 455 kilohertz. So how do we do this? Okay, so this I will show you later about that. And if you see that this is the block diagram of super heterodyne, so the super heterodyne receiver for FM is almost similar with the super heterodyne for the AM, almost similar. And it has a few other components. And if you want to see the super heterodyne, so you see that here we have a mixer will mix the signal. So we will down convert. So mixer will down convert into intermediate frequencies, and this is IF amplifier will increase the signal in terms of amplitudes. Limiter will limit in terms of voltage, and then here we have a discriminator, and then de-emphasis networks, and then to the output. Okay, so what is the limiter, discriminator? So it has been explained here. Okay, and also de-emphasis networks, similar with the AM that we have learned previously. Now we can see this picture, this block diagram. So this is the FM super heterodyne receiver. This is also known as the Armstrong receiver. So I will explain to you about this. Okay, so hopefully you can have more understanding about the process happens. Wait, So it's already 10 o'clock. Sorry, I'm gonna take a few minutes after this. So I will explain this to you so that you can have more understanding. Maybe this is also related to your project, okay? So this is a FM receiver, okay? Before that, can I get your response? Are you still there?
Yes,
Can
Doctor.
you?
Yes, Doctor.
Yes, Doctor.
Okay, thank you for the response. So I will explain about this. Okay, I will explain about this. So you see that this antenna, for example, this antenna will receive all the frequencies, all the FM frequencies from 88 megahertz until 108 megahertz. So the antenna has a very wide bandwidth. It will absorb all the signals. Okay, but we don't want to listen to all the frequencies. We just want to listen to one frequency only. Okay, so for example here, I want to listen to Era FM, for example. Era FM, which is the frequency is 104.5 megahertz. Okay, 104.5 megahertz. So whenever I want to listen to these radio stations, that means I will tune my radio at this frequency. So my radio will tune, means that it will set the center frequency at 104.5. So it is actually the job of the pre-selector to select the frequency that I want, which center at the 104.5. Okay, and if you so now I want to listen to this radio. So pre-selector will tune to 104.5, center at 104.5. Okay. Okay, so as we have as I've mentioned previously that there are two intermediate frequency. The first one is 10.7 megahertz. Could you please mute your mic so that okay. So the first IF center is at 10.7 and the second IF would be 455. Okay. So this is the thing that we need to remember. Okay, that means the first IF, the first down conversion is 10.7 megahertz, and the second IF is 455 kilohertz. Okay, so this is the center of the IF. Could you please mute your microphone? Someone is not mute. Okay. Boleh tolong mutekan you punya microphone please? Someone is not mute. Okay, so now I want to listen to 104.5. Okay, so if you remember that we can use a high side.
To mute.
Doctor, you
Sir, your
tak dengar.
mic is muted.
Okay, can you hear my voice?
Yes, Doctor.
Yes, Doctor.
Okay, sorry about that. Sejak bila mute baru
Baru ni.
Baru
Okay,
je, baru
okay.
je.
Okay, now you can see my screen, you can hear my voice.
Yes, Doctor.
Okay. Yeah. So Mana pula? Sekejap. Wait. Okay. Okay. So if the local oscillator is higher than the input radio frequency, that means we can use a high side injection equation. So this you can refer to the AM, high side injection and low side injection. So if you use a high side injection, that means we can find the FIF equal to F local oscillator minus FRF. Okay, so this is if high side injection, F high. And if the local oscillator is lower than the input RF, that means we can find the FIF equal to FRF minus FLO. So this is for low side injection. So let's say I want to use a high side injection, because most of the practical system we use a high side injection. So in this case, I can assume that the frequency of the oscillator is higher than my input frequencies. My input frequency is from 88 until 108. Okay. So now the signal has been passed through the RF amplifier. So we have limit the frequencies, center at 104.5. So we pass through the RF amplifier to amplify the amplitude. Okay. And then it will pass through the first mixer. So the first mixer will mix the signal with the first FLO1. Okay, FLO1 mix with FRF. Mix with FRF. So you see that the mixing process will produce upper sideband and also the lower sideband. Okay, so it will produce the upper and lower sideband, which is FLO plus FRF and also FLO minus FRF. Okay, so in this case, you must remember that the first IF here that we want to produce is 10.7 megahertz. So the first mixer will do the first down conversions. Okay, the first down conversions to become 10.7. So what happened now is that so what happened now is that maybe I can use this. Okay, so how much is the FLO that I want to use here? So FLO, if I want to use a high side injection, that means my local oscillator frequency would be higher. So what I can do is that so FLO that I can use for the first FLO, so FLO, the first FLO is equal to FIF1. So I just want to show you here. So FLO1 is actually equal to FRF plus FIF1, the first of the IF. Okay, so and then this is actually the FRF is the frequency that we receive, the center frequency, which is the radio station that I want to listen, 104.5 megahertz. And we plus with the first intermediate frequency that we already know from the standard, which is 10.7. Okay, because whenever we do the down conversions, we will down convert into this first IF center at 10.7. So how much is the FLO that I need actually? So the FLO that I need is actually 115.2 megahertz. Okay, this is if I use a high side injection. Okay, high side injection. That means my local oscillator frequency is higher than the input RF frequency that I want to listen. Okay, I want to listen to 104.5 and I want to produce the first IF center at 10.7. That means I need to have a local oscillator frequency at 115.2 megahertz. Okay, so from here, 115.2 megahertz. So we can see how much is the frequency that we produce after the first mixer. Okay, so the first mixer, as I mentioned, that mixer will do multiplication process. That means it will produce upper and the lower sideband. Okay, the upper and also the lower sideband. So in this case, the upper sideband produced from the first mixer, okay, from the first mixer is actually equal to FLO plus FRF. Remember, the upper sideband is FLO plus FRF. This is the upper sideband produced by the first mixer. So this is 115.2 megahertz plus the radio station that I want to listen, 104.5 megahertz. So this is 19.7. Okay, so 219.7 megahertz. So this is the upper sideband. And for the lower sideband, is FLO minus FRF, which is the first IF, which is 10.7 megahertz. Okay, so we have the higher frequency and also the lower frequency, and this is what we want actually. Okay, so it is a job of a band pass filter to select 10.7 megahertz and remove the higher frequency. Okay, so 10.7 megahertz will go through the second mixer. Okay, we'll go through the second mixer and we're going to produce the second IF, which is 455 kilohertz. So now how much is the FLO2? Okay, so FLO2 would be equal to the input, which is FIF1, okay, plus plus with the FIF2, which is 455. This is if I use the high side injection. So if I want to use a high side injection, I assume that the second local oscillator is higher than the input. Okay, the second local oscillator frequency is higher than the input frequency, which is FIF1. So what I need to do is I need to plus with the output. The output here is FIF2, the second IF, which is 455 kilohertz. Okay, this is by standard center at 455. So this is a second down conversion. Okay, so what happened here is actually equal to the input 10.7 that we have produced megahertz plus 455 kilohertz. So I have local oscillator higher than my input, which is 11.5 11.155 megahertz. Okay, this is my second local oscillator. Okay, so again, after the second mixer, we're gonna produce FUSB and also FLSB. Okay, because the second mixer will do the multiplication process. Okay, mixer will do the multiplication process. That means we're gonna produce upper and the lower. Okay, the lower would be 455. How much is the upper? The upper sideband would be FUSB from the second mixer would be equal to FLO2 plus FIF1. Okay, so remember why I do this, because mixer will have upper and lower. So now we already know the lower, which is 455. We want to find the upper frequency, which is 11.155 megahertz plus 10.7. Okay, so we produce 21.855, 21.855 megahertz. Okay, so this is for the upper sideband produced by the second mixer. What about the lower sideband? FLSB from the lower sideband would be FLO2 minus FIF1, which is equal to 455 kilohertz. Okay, so since we want to down convert, that means we can remove the upper frequency by using the bandpass filter. So the bandpass filter will remove the higher frequency FUSB, and it will let through the lower frequency, the lowest frequency, which is 455 kilohertz. Okay, then it will pass through the IF amplifier, amplify the amplitude, and then pass through the bandpass filter to remove all the unwanted harmonics, and then pass through the limiter. Limiter will limit the voltage, because it's gonna have some peak amplitude. It will limit the maximum voltage. Then finally we will do the demodulation process, either using a slope detector, balanced slope detector, or using the PLL. Okay, to produce the here we're gonna produce the VMT. Okay, we're gonna produce the VMT. So the VMT here is again VM sine 2 pi FMT. Okay, and de-emphasis here means that we're gonna reduce the voltage with the same factor that we have amplified in the transmitter. Okay, so you can see this in the AM topic as well. Okay, and this is put inside the audio amplifier and passed through the speaker. I can listen to the ERA FM, the radio station that I want to listen. Okay, this is just example. So you see that this process happens with two down conversions of frequencies. Okay, from RF frequency band, down convert into first IF center at 10.7, and then another down convert center at the 455 kilohertz. Then from there, we can do the demodulation process. Okay, so we down convert 2 times, so that easy for us to do the demodulation process. Okay. I don't know, you have question about this or not? Hopefully you understand about this. So,
Yes,
yeah, you have question to ask?
No, thank you, sir.
Okay. So, I'm not sure whether we have asked this question, but we have asked something like this, something like this example, where the student needs to know about the high side injection, low side injection. So if the high side injection means that the local oscillator frequency is higher than the input. Okay, so in my example, I'm using a high side injection. I must make sure that my local oscillator frequency is higher than the input. So that's why you see that my FLO is plus with the another thing, a frequency plus another frequency, which is higher. Okay, so since we want to do the down convert, that means we're going to take the lower frequency and remove the upper side frequency. Okay, so from this example, the key point here is that we must know what is the center of first IF and also the center of second IF. From there, we can do the calculation of the frequencies. Okay, and you see that from this is the comparison of FM and PM. So I think you can read this statement, and this is the graph for the graph for the FM comparison. So this is actually beta so beta F and beta P. So beta F or beta P. So you see that beta, the modulation index, is proportional to the VM. So remember that beta P is actually equal to Kp VM. Beta F is equal to Kf VM over FM. So both modulation index are directly proportional to the peak amplitude of the modulating signal. And if you see the second graph here, beta, so this is for, again, the modulation index versus FM. For PM, you see that for PM, beta is just equal to kpVM. It is not related with the modulating signal frequency. Whereas for the FM, the beta F is actually equal to kf VM over FM. So it is inversely proportional to the modulating signal frequency. The higher the modulating signal frequency, the lower would be the modulation index. And again, delta theta is equal to Kp Vm. Delta theta is equal to Kp Vm. So it is directly proportional to the peak amplitude of the modulating signal. And delta F is actually equal to Kf Vm. So this is delta F is actually equal to Kf Vm. So also this parameter is also directly proportional to the voltage of the modulating signal. Okay, delta F is the frequency deviation. Delta theta is the phase deviation. Okay, and then what? So there are several advantages of FM over AM. noise reduction, improve system fidelity. Fidelity means this is related to the frequency, related to the signal that attenuates from transmitter to the receiver. So we're gonna have a a better signal in terms of SNR at the receiver compared to the AM, and it is more efficient use of power compared to the AM. Disadvantage is wider bandwidth and more complex. So this is if we compare FM with AM, okay, or we can compare PM and also AM, okay. So this is for the advantage and disadvantage of angle modulation signal that we use. Oh, that's it. And I think that's all for tonight. Sorry, can I get your response? Are you still there?
Yes, doctor.
Yes, doctor.
Yes, doctor.
Okay.
Yes, doctor.
Yes, doctor.
I'm here,
Okay.
doctor.
Okay, we'll take the attendance. Yeah. Sorry, I will take the attendance. I think here we can download the. We can download the attendance here, I think.
I think so.
Sorry, first time guna sekejap. Jap. But if you want to take attendance, I also already wait. I also have this one. Wait. Sorry, we can take the attendance and then you can go out. Wait. So again, the attendance can be taken based on section. So we can go through one section at a time. Okay. So you can open your QR code. Okay, open your QR code. There. So for section 1, you can open your QR code with it. Okay, maybe wait. So maybe I will share again my screen. Okay, can you see my screen? This is for section 1, so we'll go through one by one. Section 1. Okay, section 1. Could you please scan your attendance, and then I will move to the section 2 later after this.
Thank
So
you,
in the
Doctor.
meantime, if okay, siapa yang dah attendance, you can go out, no problem. Okay, see you again next week.
Thank you, doctor.
Okay, welcome. Okay, quickly. Section 2, tunggu sekejap section 2.
Thank you, doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, doctor.
Doctor,
Yeah.
can you please read loud the QR code?
Pardon? Tak dengar.
Can you please read the number?
The number?
Yeah.
Okay, now 5237 5061. Why you cannot scan this one? 5061 9883 4491. Okay. Done? Are you done?
Doctor,
Yeah. Siapa lagi
I
belum?
can't. I
No,
can't.
doctor, I cannot.
What happened? Tak
I
nampak
think there's some problem in the map.
Wait, you can see my screen, right?
Yes, yes.
Can you see my screen?
Yes, yes.
Okay. Okay, any more? Sorry, I cannot hear you. Something wrong with the audio. Okay, so no more? 9 students? No one, eh? Okay, so sorry, section 2 now. I gotta go to section 2. There. So wait, I will go through the section 2. Wait, section 2. So section 2. Wait, section 2. Sorry for the delay. Okay, section 2. You can scan your attendance.
Thank you, doctor.
Okay, welcome.
Thank you so much,
Thank
doctor.
you, doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Doktor, saya ada satu masalah.
Okay.
Thank you, Doctor.
Boleh scan, tapi yang saya ada hantar saya punya surat pelepasan untuk 18 hari bulan Disember. So doktor dapat tak?
Okay, nanti saya adjust balik yang attendance tu. Nanti boleh ingatkan saya dalam kelas tak nanti?
Boleh, doktor.
Nanti dalam kelas tolong remind saya semula boleh? Nanti saya just take your attendance, no problem. Okay?
Okay, dok.
Nanti kita jumpa hari Ahad atau Isnin masa kelas. Nanti you bagi tahu saya lah. Boleh?
Okay, dok. Boleh.
Okay. Okay, any more?
Saya tak boleh scan.
Doktor.
Dia
Tak
kata
boleh scan.
invalid.
Kenapa tak boleh scan ni? Alamak. Boleh tak? Boleh scan? Siapa nama?
Saya Wazin.
Number?
Going down.
Doktor, saya punya internet slow. Dia lambat nak scan.
Down.
Ya ke? Nama siapa?
Doktor.
Okay. 28.
I cannot hear your voice. What happened?
38.
Okay, one by one please.
Right.
Doktor, saya punya internet lambat. So dia bila dia nak scan tu dia jadi lambat.
Okay, nama siapa?
Nama saya Najwa Balkis.
Najwa Balkis. Okay, done.
Tak ada dalam tu. Bawah, doktor.
And then what? And then siapa lagi?
Saya, doktor.
Lagi doktor.
Your name?
Muhammad Irsyad Hakimi, 18.
Nama Najwa Balkis. Nombor 36.
36. Okey, dan
36.
Irsyad dah 36 dah. Najwa Balkis sudah.
Najwa Balkis, doktor.
Sudah. Najwa Balkis dan.
Thank you, Doktor.
Okey, welcome.
Doktor, saya section 1, doktor.
Number
Nombor?
36, doktor.
30?
Najwa Balkis.
Sudah. Najwa Balkis sudah.
Betul, doktor.
You tak nampak skrin
Betul,
eh?
doktor.
I think I share my screen, right? Can you see my screen?
Ya.
Doctor, can you take my attendance?
Number what now?
38.
Thank you, doktor.
Okay, welcome. Okay, dah.
Doctor, can you
Apa
take
lagi?
my attendance?
Sorry?
Can you take my attendance? I'm
Yeah.
Omar.
Number? Your name?
Go down. Yeah.
Omar.
37.
Okay, Omar. Okay,
Thank you,
done.
doctor.
Okay, welcome. Next.
Doktor, saya section 1, doktor.
Section 1. Section 2 ada lagi tak? Tak ada
Saya, doktor.
Siapa nama?
Puak. 38.
Okay, Puah dan. Okay, ada lagi section 2? Tak ada. Okay, saya pergi ke section 1 sekejap. Tadi section 1 siapa yang belum?
Bawah sekali,
Section
doktor.
1. Nama?
Yumni.
Nombor berapa nama?
Bawah sekali.
Oh, bawah sekali. Okay. Jap. Yumni. Okay, done. Siapa lagi? Section 1.
Ya, doktor. Nufakira.
Nama? Fakira. 44 ni Okay, Fakira dah.
Thank you, doktor.
Okay, welcome. Siapa lagi? Semua dah Any more? So, if no more, siapa lagi Fakira dah. Tak ada lagi
Okay, thank you, doktor.
Okay, welcome. So we can stop recording.